Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we had learned how are we going to take a shift from the classical approach of summation type expression to a vectors and matrices. And then we had obtained the reduced normal equations. And now you have understood that these reduced normal equations can be obtained in two different ways. In case if we are interested in a testing of hypothesis related to the treatment effects, then we are going to eliminate the block effect, we are going to obtain the estimates of treatment effect, and then we are trying to obtain the normal equations. So, we had finally obtained the reduced normal equation where we have used the adjusted treatment totals. And now you can see that why we are using the terminology here, the adjusted treatment totals. Because we are trying to adjust the treatment totals by the block effects. So, now if you try to observe the nomenclature, then it will be very easy for you to understand the second type of estimation in which we are going to eliminate the treatment effect and we are going to estimate the block effects. So, this type of hypothesis is going to be more useful when somebody is interested in testing the hypothesis for the equality of the block effects. Well, as a statistician, you have to develop both the tools for the testing of treatment effects and for testing the equality of block effects. This is the choice of the experimenter that in a given condition what the experiment wants. So, with this point of view, in this lecture, first I will try to now develop here the reduced normal equations when we are trying to opt for the second approach, which was we will try to estimate the block effect after eliminating the treatment effect. And then now you can say you will obtain here one more type of reduced normal equation in which you are going to use the adjusted block totals. If you try to compare the nomenclature, you can be clear what are you going to get. So, you will have here the adjusted block totals, and why they will be called as adjusted block totals? Because you are going to adjust the block totals due to the fact that you have removed the treatment effects. And after that we have obtained that type of reduced normal equation, then you will have both types of setup, one in your hand this is for the treatment and another for the blocks, and depending on whatever you want you can do it. And after that I will try to show you how you can develop the analysis of variance table and what are the things which you have to be careful. So, let us begin our lecture. Okay, so, now just for the sake of quick review, if you try to recall that in the last lecture we had considered the model y I j m is equal to mu plus beta I plus tau j plus epsilon I j m, where I goes from 1 to b, j goes from 1 to v, and m goes from 0 1 up to n I j. And then we had obtained the normal equation by minimizing the sum of its squares due to the random errors, say here capital S. So, we had partially differentiated S with respect to mu, alpha I, beta j, and we had obtained these three equations, rather three sets of equation which are all together b plus v plus 1 equation, and they were clubbed and they were expressed in the form of a vectors and matrices, like as here this equation is star. And then you had obtained the three different sets of equation from this star, and you had the equation number first, second and third. Now, from this equation number first, second and third, you have now two options. You try to eliminate beta and then you try to obtain the estimate of tau from the equation number 3 or vice versa. So, we had opted for the first approach in the earlier lecture, that from this reduced normal equation or reduced intra-block equation, we had pre-multiplied the equation number 2 by the quantity n transpose k inverse, and then we had subtracted it from the equation number 3, and we had obtained this result, that V minus n transpose k inverse B is equal to R minus n transpose k inverse n into tau hat. And this was written here as a q is equal to theta, where q is given by this expression V minus n transpose k inverse B, and C is given by the expression R minus n transpose k inverse n, and this vector q is called as the vector of adjusted treatment totals, because it contains the treatment totals which are adjusted for the block effect, and this C matrix that is called as C matrix itself. Now, if you try to see that in order to obtain the reduced normal equations for the treatment effect, now we are giving it a name. What we have done, we have first estimated the block effect from one of the normal equation and substituted it into another normal equation related to the treatment effect. Here you have to be careful little, it is not one normal equation, but it is something like a set of say normal equation, which I am just calling for the sake of simplicity and for the sake of understanding as the normal equation. Right. So, this way what we have done, we have obtained the adjusted treatment total vector q. And why this is called as adjusted? This is very important for you to understand and learn. This is adjusted for block effects, right. And now, the next question comes, can you repeat the same thing for the block effects also? And can you obtain the reduced normal equation for the block effects? Yes. What we will try to do here, that we are going to now estimate the treatment effect from one of the normal equation and substitute it into another normal equation related to the block effects, and we will obtain the reduced normal equation for the block effects. How? Let us try to see. In case if you try to recall, we had earlier considered these equations, and now we are going to do the same exercise what we have done earlier. But now we are going to find out the estimate from the equation number 3 first. So, if you try to see what we try to do here, that in this equation number 3, if you consider, or equation number 3rd, you try to pre-multiply on both the sides by n R inverse. You can see here now this quantity, that last term here, that becomes simply here tau hat, and then we can obtain the tau hat from here, and this tau hat can be replaced here, right. So, this is the same process that we did earlier for the beta hat between equation 2 and 3, but now we are going to do it between 3 and 2. So, now we try to pre-multiply the equation 3rd by this quantity, and we obtain this quantity here, and then we try to subtract it from the equation number 2nd. And then if you try to see here, you get here this quantity B minus n R inverse V is equal to K E B 1 minus n R inverse R E V 1 mu hat plus A minus n R inverse n transpose beta hat plus n minus n R inverse R tau hat. You can see here this term becomes here identity matrix. So, this becomes here n minus n, which is here a null vector. And similarly, if you try to solve it here, this R inverse R becomes here I identity matrix, and then this, if you try to find out here the value of n into EV1, this will come out to be the same as the value of k into EB1. And if you try to recall, we have done this exercise in the beginning of the last lecture. So, this will again become a null vector. So, this term will only appear. So, this is here like this, P minus n R inverse V is equal to K minus n R inverse n transpose into beta hat. So, now I can do the same thing as we have done it earlier. I will try to express this equation as d beta hat is equal to p. So, now you can identify here that this quantity is going to be here, see here p, and this quantity here is going to be here d, right. And if you try to see, the names are given so that you can identify them. Earlier you had called this quantity which you are calling here as say p, that was something like q, and earlier you had a matrix C, but now you have a matrix here D. So, that is why now you can identify what are this P and D, and just like you had identified the Q and C, right. So, if you try to recall that in the earlier case we had obtained the reduced normal equation as Q is equal to 3 tau hat, but now we have obtained here the reduced normal equation as d beta hat is equal to p. So, now you get here this p here as a adjusted block totals. And now you have to understand, that is more important actually here, to know that why this is called as adjusted. If you try to see in the case of RBD, you did not had this adjusted treatment totals or adjusted block totals, because all the equations were estimable, you could use parameters without any problem. So, that is why there was no difference between so called adjusted or say unadjusted. But now here you can see, because this is going to make a difference, because it depends whether you are first trying to estimate beta and then trying to eliminate tau, or vice versa, right. So, that is why this p is called here as a adjusted block totals, and this is called adjusted because this is adjusted for the treatment totals, right. And in this case, this D is going to be the same matrix as you had obtained earlier, right, and P is going to be here like this, which you obtained here earlier, and beta hat is the vector of all the estimators of block effects, beta 1 hat, beta 2 hat, beta b hat, right. So, now you can see here, this is another sort of reduced normal equation, just like Q is equal to C tau, right. So, now it is very clear that whenever the objective is to conduct the test of hypothesis related to the equality of treatment effects, we are going to estimate the parameters from the reduced normal equations Q is equal to C tau. And when the objective here is to conduct the null hypothesis related to the equality of block effects, then you are going to estimate the parameter from this normal equation, that is d beta hat is equal to p. This is very important point for you to understand. How this is going to affect the analysis of variance, this is my now next step to show you. But this concept should be now settled very clearly in your mind. I will repeat once again that when the objective is to conduct the test of hypothesis for the equality of treatment effects, you are going to use the reduced normal equation for the treatment totals, and when the objective is to estimate to conduct the analysis of variance for the block effect, or you want to test the null hypothesis for the equality of the block effects, then you are going to use the reduced normal equation for the block totals. And based on their estimators, you are going to conduct the analysis of variance. So, obviously, now you can see that you are going to have two types of analysis of variance, one for the testing of block effects and say another for the testing of treatment effects. Now, how they are related and why this is happening, that is now our objective to understand in this lecture, right. So, now my first objective now after this introduction to reduced normal equation is how are you going to conduct the analysis of variance, right. So, now I believe that we already have discussed a lot that how are you going to construct the test statistics using chi-squared distribution, that you try to take two variables which are chi-square, which are independent, then you try to define the F statistics. All those things now you know. If I simply tell you the result, I hope that will help you, because if I try to repeat the same thing again and again, you will lose the interest in the lecture also. So now I am trying to show you here that when our objective is to construct the analysis of variance test for testing the hypothesis for the equality of treatment effects, then how are we going to proceed? The main thing what you have to learn here, that how are we going to obtain the sum of square due to block, how are we going to obtain the sum of square due to treatment, and how are we going to obtain the sum of square due to errors, SSE. That is very important for you to understand, that how are we going to get it, and then I will try to explain you why we are trying to do so. And you will see that this result or the approach, it is going to be different from the approach what you did in the case of say complete block design analysis, like as in the case of randomized block design. So, how to get it done? Please try to concentrate and try to see very clearly in this slide. Okay, so now let us begin. So, now we know that whenever we want to conduct the analysis of variance, we have to obtain sum of square due to blocks, and then sum of square due to treatment, and then SSE, and then based on that you have to use the Fisher-Cochran theorem, so that you can write down in the write down their sum as TSS. Remember, I am once again saying that we want to use here the Fisher-Cochran theorem. Now, let us move and try to see what happens. So, now first you have to observe and have faith on me for a couple of minutes, and then after that I will try to show you that why I was doing like this. So, I am trying to divide this discussion into smaller parts. So, now we want to consider the null hypothesis H naught tau equal to 0, right. Now, as you have learned in the case of a two-way analysis of variance and one-way analysis of variance, that in some sense when you try to conduct the two-way analysis of variance, that is equivalent to a sort of one-way analysis of variance, right, because but it is not, they are different, but just try to think for a while, right. So, first we try to find out the sum of squares due to blocks, right. So, if you remember that in a two-way classification, how you had found the sum of squares due to block? For example, in the case of a randomized block design, it was something like summation I goes from 1 to b, bi square upon ki minus g square upon n. Now, remember one thing, that in the case of RBD, you had taken all the blocks of the same size. So, ki was equal to k there at that time, some means equal values, right, all k1, k2, kb were same, right, or I can write down here ki was equal to kj for all I not equal to j. Now, you want to translate that expression to your setup. So, I can write down here, say here summation I goes from 1 to p bi square upon ki, where ki is the number of plots in the ith block, minus the correction factor g square upon n. Now, your job here is to convert this summation bi square upon ki in the format of a vectors and matrices, because now we are doing everything in terms of vectors and matrices. So, and at this moment we are trying to learn that how we are going to switch from the classical approach to the approach of vectors and matrices. So, that is why I am trying to show you here all these steps very clearly. Once you are convinced, when you are comfortable, I can write down all these steps simply directly. So, now if you try to look at this term, summation bi square upon ki. If I try to write down here a vector like b1, b2, bb, and if I write down here a matrix which is a diagonal matrix of the elements 1 upon k1, 1 upon k2, 1 upon kb, and then this is a column vector b1, b2, bb. If you try to solve this thing, don't you get the same quantity? Summation I goes from 1 to p bi square upon ki? Yes. And now if you try to see what was your here this vector b1, b2, bb, that you had indicated by vector b. So, b here is like this vector of b1, b2, bb, and then if you remember what is your here this diagonal matrix here. Do you remember that you had defined a matrix K, which was the diagonal matrix of K1, K2, Kb? So, obviously, if you try to take here K inverse, this is once again going to be the diagonal matrix of the elements 1 upon K1 up to 1 upon Kb. So, now you can write down here this diagonal matrix here as a K inverse, and then this B will come over here like this. So, you can see here you have obtained the sum of squares due to block as say here B transpose K inverse B minus G square upon n very easily. There is no confusion on this thing, right. Now, we try to obtain the sum of square due to error. Now, if you try to recall your basic fundamental that we discussed in the beginning of the course when we were trying to do the one way and two way analysis of variance, the error sum of squares was obtained just by substituting the values of all the parameters in the sum of square due to residuals epsilon in ij's. So, this will be here triple summation y I j m minus mu hat minus beta I hat minus tau g hat. And now, you simply have to use the normal equations that we had obtained earlier, and you can write down this quantity as here like this, right. Well, you can just look back into your earliest these equations and you can write down very easily. And now, if you try to open this equation, this will be here like this triple summation y square I j m minus mu hat and then this g, and then here summation tau j hat into E j, and then summation beta I hat into B I. We already have done this exercise when we were trying to obtain the normal equation using the summation approach. And if you try to see, this normal equation can be written here like this. This sum of squares due to the observations, this can be written here. For example, you can see here if you have here a vector like y1, y2, yn, and if you try to write down here like this, suppose y transpose y, you can see here this is something you are here summation yi square. So, this can be written here as a y transpose y, this mu transpose g will come like here this, and you already have written this summation tau j hat v j has say here v transpose tau hat, and this term here summation beta hat I b I can be written as here b transpose beta hat. And now, if you try to recall your original normal equation that we had obtained, if you try to see here, right, because equation number here 2, if you try to obtain here, if you try to see, I have written here, right. From here you can obtain the value of beta hat is equal to k inverse b minus E b 1 mu hat minus k inverse n tau hat. Now, you please try to substitute this value over here, right. Try to substitute this value here in place of beta hat, right. And let us try to see what we obtain here. Now, if you remember, we had done some small algebra. Well, if you wish, you can do it here once again. If you try to see here that V transpose E1B, that this is actually the sum of all the treatment totals, and when you try to write down the quantity like B transpose EB1, this is the sum of all the block totals, which is coming out to be here as a G, which is the grand total of all the observation. So, now we use this result, and now we have substituted the value of beta hat here, you can see same value which you have obtained, and now we simply try to simplify it, nothing more than that. Very simple job that we are going to do here, right. So, now if you try to see here, this can be written here as say y transpose y minus g mu hat, and then if you try to bring this B transpose inside the bracket, this will become here B transpose K inverse B plus G mu hat plus B transpose K inverse and tau hat minus V transpose tau hat from here. Right. Now, if you try to see what is happening, this G mu hat and G mu hat, they are getting cancelled, right. And then what you have here? You have here two terms which are related to tau hat, this one and this one. So, we try to club both the terms together for this tau hat. So, this will become here B transpose K inverse n minus V transpose into tau hat. And then the remaining term we have here y transpose y minus B transpose K inverse B. Now, I try to do here one thing, that I try to add and subtract here the correction factor g square upon n, and then I try to adjust this correction factor 1 here, and I try to transform y transpose y as y transpose y minus g square upon n, and the second term B transpose K inverse B as B transpose K inverse B minus g square upon n, right. So, now if you try to see what is this thing SAC, and as you can recall that once we had discussed that what is the role of correction factor. The role of correction factor is that it is trying to convert the particular expression in the form of a quadratic form, and then it is easy for us to use the results from the distributions of quadratic form and to find out the distribution of the final test statistic, right. So, if you try to see here what is really happening here now, this I have written here like this. So, now if you try to identify, you have done right from the beginning, you had written TSS is equal to SS block plus SS treatment plus here SS error. Now, you are trying to write down here SSE is equal to TSS minus SS block minus SSE. Now, from this expression, your job is now to identify what is here TSS, what is here SS block, and what is here SSE. So, you can see here, this is simply your here what TSS, and in case if you try to identify the second term, what is here this? You have just obtained here this quantity. This was your here sum of square due to blocks. So, this is your here sum of square due to blocks. Now, what is your opinion that what this third quantity is going to be? Obviously, this has to sum of square due to treatment. So, now you can see here that in the case of complete block design analysis, you had obtained the same expression, but in that case if you try to compare with this case, then TSS and SS block, they have got a similar structure, but sum of square due to treatment is changing. Now, this is a very important result for you to understand that what is this happening, and if you try to recall, ultimately you are going to apply here the Fisher-Cochran theorem. So, obviously, this these terms TSSS, sum of square due to block, treatment, SSE, etc., they have to be orthogonal to each other. So, now if you try to think from this point of view, what you have written here? You have written the SSE as like this. SSE, I am trying to denote here this error sum of square as by here SE, and you have to keep in mind that the analysis of variance what we are now going to do, this is actually the intra-block analysis of variance. So, this SE will be indicating the SSE which is obtained from the intra-block analysis of variance. So, that is what you have to keep in mind, that this symbol, this is SSE in the intra-block analysis. And what is this intra-block analysis? This is whatever we are doing here, this is actually intra-block analysis, right. So, now you have partitioned it into total sum of squares like this, block sum of squares like this, and you can see here what is this quantity V minus n transpose K inverse B. This is simply your here Q. So, the last term is coming out to be here, this is Q transpose tau hat, which has to be the treatment sum of square. So, now you are calling the first quantity as a total sum of squares, then minus block sum of squares minus treatment sum of squares. But now you can see this treatment sum of squares is different from the way you had obtained the treatment sum of squares in the case of complete block design ANOVA. For example, if I say the way you have obtained here the sum of squares due to block, here what you have done? You have borrowed the expression of the block sum of squares, and then you have modified it for the cutoff of incomplete block design by choosing different KIs, and then you have converted it into a vectors and matrices. But in case if you try to do the similar analysis with the treatment sum of squares, then possibly you are not going to get the expression like what you have got here, in this case as Q transpose tau hat. So, now the question here is this sum of square, which is the treatment sum of squares, this is based on the adjusted treatment totals. So, this is called as adjusted treatment sum of squares. And why this is adjusted? It is adjusted for the blocks. Now, once you are trying to call this treatment sum of square as a adjusted, then obviously, if you try to see when you are trying to consider the block sum of square, you have not made any adjustment. So, that is why this block sum of square is termed as unadjusted block sum of squares. Now, there is no change in the case of TSS, that is the total sum of squares, and error sum of square, they also remain the same, means the way they have been obtained earlier, means they are once again obtained exactly in the same way. So, now you can see here what you have observed here. When you are trying to conduct the test of hypothesis for the treatments, then you are obtaining the total sum of squares, which is being partitioned into sum of square due to block, sum of square due to treatment, and sum of square due to error. But what is happening between sum of square due to block and treatment? You are obtaining the sum of square due to treatment as adjusted sum of square due to treatment. But the block sum of squares, that is obtained as unadjusted block sum of squares. So, now if you try to see, when you are trying to consider the test of hypothesis for the treatment effects, then you are trying to find out the adjusted treatment sum of squares and unadjusted block sum of square. Similarly, in case if you are trying to conduct the analysis of variance for the test of or the test of hypothesis for the equality of the block effects, then in that case you are going to obtain the block sum of squares as adjusted block sum of squares and the treatment sum of squares as unadjusted treatment sum of square. So, now the rule is very simple. Whatsoever hypothesis you are interested in, try to obtain the sum of squares as adjusted versus unadjusted, and whatever is the hypothesis corresponding to that, the sum of a square is going to be adjusted and the other is going to be unadjusted. Why this is happening? I will try to show you. But before that, the degrees of freedom associated with these different sum of squares, they will remain the same as we have done earlier, because they are based on the Fisher-Cochran theorem. So, the block sum of squares, which is here unadjusted, they will have b minus 1 degrees of freedom. The treatment sum of squares, which is now adjusted, this will again have the same degrees of freedom what we had learnt earlier, because of the same reasons also, and total sum of squares will have the same degrees of freedom and minus 1, and error sum of squares will have the degrees of freedom which are obtained by subtraction, which will come out to be n minus b minus v plus 1. Right. Now, the reason for this thing, why this is happening. Right. So, first of all, you have to you can actually very easily verify that here the adjusted treatment sum of squares and sum of square due to error, they are independently distributed. They are following a chi-square distribution with v minus 1 and n minus b minus v plus 1 degrees of freedom respectively. So, now you can recall that once you have two independently distributed chi-square random variables, you can define or you can use the properties of F distribution, and you can define here F statistics like this, that under H naught Q transpose tau hat, which is the adjusted treatment sum of squares divided by the degrees of freedom v minus 1 upon SE, which is your here SSE divided by the degrees of freedom. This will follow a central F distribution with v minus 1 and n minus b minus v plus 1 degrees of freedom. So, now how to take the decision for the hypothesis H naught tau 1 equal to tau 2 equal to tau v equal to 0, that you can do very easily. You can make the decision rule very easily, and I am confident that you can do it. But the main important point which you have to understand here is that what is the difference between the analysis of variance which you conducted in the case of complete block design and now you are doing it in the case of incomplete block design. So, in the case of incomplete block design, it matters whether we are estimating the block effect first and then we are trying to estimate the treatment effects, or first we are trying to estimate the treatment effect and then we are estimating the block effects. Whereas, if you try to recall in the case of complete block design, it does not matter at all whether you are first trying to estimate the block effect and then treatment effect, or first the treatment effect and then the block effect. And that is why the testing of hypothesis related to the block and treatment effects can be done from the same estimate in the case of complete block design. But since this is different in the case of incomplete block design, so we will have two different types of analysis of variance. So, now you can see here whatever you have done here, you can compile this in the form of an ANOVA table. So, in case if you try to recall, this ANOVA table is just like the ANOVA table which you did in the case of complete block design. The only difference is that how the sum of square due to treatment and blocks are going to be defined. So, we have the same sources, treatment, blocks, error and total, and then they have their degrees of freedom like as earlier, b minus 1 for treatment, b minus 1 for block, n minus 1 for treatment, and by subtraction you can find n minus b minus v plus 1 for error. And then we are trying to find out the sum of squares. So, sum of square for the treatment, very important part, you are going to obtain by Q transpose tau hat, which is going to be adjusted, and you are going to find out the sum of square due to blocks by the term B transpose K inverse B minus correction factor, which is unadjusted blocks sum of squares, and then SSE, this is going to be obtained by subtraction, and then the TSS remain as earlier, Y transpose Y minus G square upon N, the correction factor. And now you can see here we are defining here only one mean square related to the treatment between treatment and blocks. Means earlier, if you remember, you used to define mean square for the treatment and mean square for the blocks. So, we are defining here only the mean square for the treatment, and then obviously you need to have the mean square for the error, which is SE by divided by the degrees of freedom. Right, there is no mean square here for the mean squares due to blocks. And if you try to take the ratio of the mean square due to treatment and mean square due to error, you can obtain the F statistics, right. So, this is what you have to be careful. Now, in case if I ask you, suppose you have to conduct the analysis of variance for the block effect, then what will happen? The treatment sum of squares, that is going to be unadjusted, block sum of squares, that is going to be adjusted, and then you are going to get here the MS blocks, the MS treatment will not appear there, yes, MSE will appear there, and then you are trying to construct here then one more test statistics, which is going to be the ratio of mean square due to blocks and mean square due to error. And then you can conduct the test of hypothesis for that one, right. So, now the simple question comes, why I am trying to repeat this again and again, that you need to have two different analysis of variance in the setup of an incomplete block design. So, before I try to explain you, if you try to look into this column of here sum of squares, this one, you can see here that in this case the total sum of square is equal to sum of square due to treatment, that is adjusted, and sum of square due to block, which is unadjusted, and plus SSE, right. So, the reason that why we are trying to do so and why we are trying to conduct two different types of test statistics or analysis of variance for the two hypotheses, which is just different than the case of complete block design, because in the setup of incomplete block design, there are two options. Either the adjusted sum of squares due to treatment and the unadjusted sum of square due to blocks and the corresponding sum of square due to errors are orthogonal, right. You have to concentrate on these two, means adjusted sum of square due to treatments and unadjusted sum of square due to block. Well, SSE will always be there, they are orthogonal. Or the second option is this, that adjusted sum of squares due to block, the unadjusted sum of square due to treatments and the corresponding sum of square due to errors, they are orthogonal. So, you can see here that when TSS is going to be partitioned into sum of square due to block, treatment and errors, then between blocks and treatments, one of them has to be unadjusted and say one of them has to be adjusted. So, that is why when you are trying to consider the treatment sum square to be adjusted, then obviously if you want to satisfy the Fisher-Cochran theorem, then the block sum of square has to be unadjusted. And say, and in other case, if you are trying to consider the adjusted sum of square due to blocks, then in case if you want to apply the Fisher-Cochran theorem, then the treatment sum of squares, which is unadjusted, that is going to be orthogonal, and SSE remains orthogonal in both the respective cases. So, that is the reason, right. So, in case if you try to just rewrite the same thing, you can write here error sum of square is equal to total sum of squares minus SS block unadjusted minus SS treatment adjusted, or you can write total SS minus SS block adjusted, which is now different than earlier, minus SS treatment, which is unadjusted, which is again different than earlier. So, either this will hold true or this will hold true. So, you have to choose one. Means in case if you try to take here this sum of square due to block and treatment to be both to be adjusted or say both to be unadjusted, then they are not going to be orthogonal in the case of incomplete block design. And this is important for us so that the Fisher-Cockram theorem holds, and then we are in a condition to give the or construct the analysis of variance table, and we can construct the F statistic, because F statistics is based on the orthogonality of sum of squares and SSE, right. And anyway, you need to use the Fisher-Cockram theorem so that you can partition the total sum of squares into the sum of squares due to different factors which are affecting the outcome. So, which are here blocks, treatments and random errors. So, that is how you have here these two setups. Now, it is very clear that in case if you are interested in testing the null hypothesis about the treatment effects, then you have to use this result, right, where your sum of square due to treatment that is going to be adjusted. And in case if you are trying to conduct the test of hypothesis for the block effects, then you are going to use this result in which the sum of square due to blocks they are adjusted, as simple as that, right. And you can see here one result just for the sake of completeness, that because C into EV1 is equal to a null vector. So, C is a rank deficient matrix. You can see here C is a V cross V matrix, and we are trying to say that all the row sums and column sums they are 0. So, that means C is a rank deficient matrix, and if you try to obtain here this Q transpose EV1, that means sum of all the adjusted treatment totals, you can solve it here. If you try to write down here Q here as say V minus N transpose K inverse B, and if you try to post multiply by here EV1, this will come out to be here V transpose EV1 minus N transpose K inverse B whole transpose into EV1, and if you simply try to solve it here, this will come out to be here, this term will become here summation Vi, and this term will become here simply B transpose K inverse K transpose, right. And now in case if you try to solve here them further, just try to substitute all these values over here, and you can find out that this quantity comes out to be simply here summation over J Bj, that means sum of all the block totals. So, sum of all the treatment totals and sum of all the block total, that is simply your here the sum of all the observation. So, G minus G, this is equal to here 0. So, one can say that the intra-block equations are consistent, right. Now, once we have seen that the rank of C is not going to be a full rank, that means C is a V cross V matrix, and the rank of C is, at least we know that it is not equal to V, right. So, now the question comes here, what is the rank of C? Now, you can see here the rank of C depends on different types of constraints, but we are going to confine our attention to those designs, those types of block designs for which the rank of C is equal to V minus 1. And you can see here that we have found at least one constraint, that some of row or elements or some of the all column elements in the C matrix, they are 0. So, that is why we know that at least the rank is deficient by 1. But how much it is really deficient, that is not known to us at this stage. But we know that at least the rank is not going to be a full, and it is deficient by at least 1 unit. And you will see here later on that when we are trying to consider the rank of C to be k minus 1, that is going to solve many such problems, and that is going to be helpful for us. So, we are going to consider here those types of design where the rank of C is equal to V minus 1. And these types of designs, they are called as connected designs, for which all contrast in the treatments, that is all linear combinations L transpose tau, where L transpose EV1 is equal to 0, that means they are the contrast, have unique least square solution, and this can be very easily proved. Right. So, now well, this result can be proved very easily, but then anyway I will skip this proof here, because now we are going to in some more details where we are trying to connect here different types of concepts, and then our aim is that how are we going to join them together. So, that is why now I am trying to concentrate more on the part that how I am going to join these simple concepts together, so that at the end of the day you are 100% clear the why something was happening and what was the reason and why we were doing like that. And I believe that once you understand, then the life becomes very simple. So, now we come to an end to this lecture, and this was a very important lecture where we have discussed very important aspects. The first thing what you have understood, that why this is happening in the case of incomplete block design, that we are trying to consider two different types of analysis of variance, one either for block effect or for the treatment effect. But now this reason is clear to us that the way it was happening in the case of complete block design, that both block sum of squares and treatment sum of squares, they were getting orthogonal, they were independent of each other. This is not happening in the case of incomplete block design. But what is happening? The two sum of squares are going to be orthogonal to each other only when one of them is adjusted and say another of sum of square is unadjusted. Only then they are orthogonal. Although we are going to prove all these things in the forthcoming lecture, but at this moment you have to just accept it as such. And this is the reason that whenever we want to conduct the test of hypothesis for the equality of the treatment effects, we will have an analysis of variance where we are going to consider the adjusted treatment sum of squares. So, obviously, the block sum of square is going to be unadjusted. And similarly, when you are trying to conduct the analysis of variance for the equality of block effects, then you are going to consider the adjusted block sum of squares, and obviously then the treatment sum of squares has to be unadjusted, so that it is orthogonal for the application of Fisher-Cochran theorem. Now, you will see that in most of the books people are more interested in finding out or in getting the results for the analysis of variance for the treatment effect. That is obvious, means from the application point of view, as I said in the beginning, that people are more interested in the equality of the treatment effects. People are not that much interested in the case of block effects. So, that is why only we are considering more, or we are putting more emphasis on the results which are related to the null hypothesis related to the equality of treatment effects rather than the block effects. But this does not mean that the analysis of variance for the block effects cannot be developed. We can develop it very easily, exactly on the same lines as we are trying to do for the case of treatment effects. So, that concept should be clear in your mind. So, you try to look into this concept, try to revise it, try to understand it, and most importantly try to do this algebra with your own hand, own pen, own paper, using your own brain. And this will make you more confident, and in the next lecture I will try to discuss some properties, and then I will try to relate those properties with the analysis what we have done. So, the next lecture is going to be dependent on whatever we have done. So, it is very important for you that you revise this lecture, and I will see you in the next lecture. Till then, goodbye.